Hello, welcome to today's training on creating an entopology workflow for the design of custom-fit prosthetic limbs. My name is Kelsey Hines. I'm an onboarding engineer here at Entopology, and I will guide you through today's session. If you haven't already, you can download the zip file below, which contains part files, entop files, and slides with today's material. As we move through today's session, you can use the controls in the bottom right corner of this video to speed up and slow down as needed. Throughout today's session, we'll review a couple of different entop functionalities that are really helpful in patient-specific applications such as this. First, we'll import 3D scans to ensure a custom-fit socket on each of these prosthetic limbs. Then, we'll lightweight the limbs to ensure patients' comfort and mobility. After that, we'll apply texturing to aid in traction with the ground. Finally, I'll demonstrate how to use this newly created workflow to streamline the design process down the road, reducing design time of these custom-fit prosthetic limbs from hours down to just a couple of minutes per patient. A good practice when creating a workflow in Entopology is to label your first section geometry. And in this section, I like to house any imported meshes, CAD parts, or any variables that I might want to come back to frequently throughout the creation of my workflow. Now, I'll add a couple of sections to show you exactly what I plan to cover in today's training. And I can rename all of these sections by double-clicking and writing over section names. So after our geometry section, we'll want to create and customize this socket given the 3D scan of the patient's data. So I'll call this socket creation and customization. After this, I'll want to lightweight the prosthetic leg. Then I'll want to texture the sole of the foot for better traction with the ground. And finally, I'll want to orient all of these parts relative to one another and create a final assembly. Now, any new additions to an Entopology workbook, any imports or new blocks will fall where this white line is in the notebook. So I'll pull this white line up to the geometry section and place it there using a single click. So now anything that I import or any new blocks that I pull in will fall exactly where this white line stands. So I'll begin by importing our two 3D scans. One is a solid scan of the patient's residual limb, and the other is the same limb, but a surface scan. We can play with the visibility of these and take a look at both of these 3D scans. And I'll go ahead and make these into variables by right-clicking and selecting Make Variable. And I'll just call these Solid Mesh and Surface Mesh. After making these variables, I'll want to create implicit bodies from both the solid and the surface meshes. Implicit bodies are Entopology's native format, and it'll be easier to modify and make any customizations to these bodies by creating implicits. So I can pull new blocks into here by either searching implicit body from mesh and taking a look at this contextual search, choosing that from the drop-down. So I will create an implicit body of that solid mesh, or you can take a look at this upper ribbon and go to your Utilities tab and create this implicit body from mesh here. That'll pull the same block into your Entopology workflow. So here you can see this solid mesh, And when I isolate the implicit body from that same mesh using the hotkey I, you see an implicit body with no triangulation or boundaries or edges. I'll create a variable out of this and call this implicit solid. Likewise, I'll create a variable here called implicit surface. After I've got these implicits made, I'll pull in the remainder of the prosthetic, which will be this prosthetic leg in a step file. You see that the remainder of this leg isn't oriented correctly to the scan, and that's okay. Later on in our assembly portion, I'll show you how to orient that properly using list processing. So when we do import this CAD part, sometimes you might see a warning here. Assemblies aren't currently supported by Entopology, so they show up as flattened, but you can go into the Properties tab in the block details, and you can see all of these individual bodies. You can pull out any of these chips into your workflow and treat them like regular CAD parts. Since I am familiar with this CAD assembly, I know that bodies 1, 8, 9, and 10 are those I want to manipulate in NTOP. So I'll go ahead and pull these into our workflow. The remainder of these parts are screws and connectors that don't have any use for within the NTOP platform. So I'll pull out 1, 8, 9, and 10, and I can rename these CAD variables by isolating them. This is going to be our upper hinge, so I can double click and rename this to upper hinge. Isolate our next part using I. This is our lower leg that we plan to lightweight down the line. Next is our heel. And finally, our toe. Because I want to manipulate each of these 4 CAD parts within Entopology, I'll want to create implicit bodies for each of these parts, as I did for the surface mesh and the solid mesh before. So I'll pull in a couple more of those implicit blocks, implicit from CAD body this time rather than mesh. And I can copy and paste a couple more instances of those into my notebook. I'll pull each of these into the blocks. And if I take a look at all 4 of these with the visibilities on, you can see that we've lost our boundary representation that we had in our CAD parts, signifying that these are all implicits now. I'll go ahead and make variables and rename all of these so I don't have to do that later on down the line. And I'll just name them the same thing as these CAD parts because now they have a differentiation between an implicit and a CAD that we can use later in the workflow. Once I've created implicit bodies out of all of these, I can clean my workbook up a little bit, minimize some of these sections to allow for easier reading, and we have completed our geometry section. Now that we've completed our geometry section, I want to move forward into socket creation and customization. So I'll single click to drop this white line into our new section, and I'll add a new block called thicken body. This block will take any body that has 0 volume and thicken it to a specified amount. So the body I want to modify here is our implicit surface. So I'll drag and drop that variable. And if I give it a thickness of 3 millimeters and hit enter, you can see that that initial implicit surface with 0 volume now has a thickness of 3 millimeters. Now, instead of a scalar variable like that 3 millimeters, we can see by this icon that the thickness can also be driven by a field. So instead of 3 millimeters, if I chose to put a ramp into here, then I can use a scalar field. I'll drive this with a plane from normal. So I've got 2 inputs with that plane from normal. I've got the origin and the normal direction. Let me go back and turn the visibility on for my implicit surface to see exactly what we're doing here. And I see that this normal is in the positive z direction, which is what I want. But the origin is at 0, 0, 0, and I'd like the origin to fall at this minimum z direction for this implicit body, this new thickened body. So I can add a point to this origin and keep that x and y 0, but in the z direction, I can open the bounding box of our implicit surface by opening the block details and choosing this bounding box dropdown. And I'll take the minimum point in the z direction. Now we can see that this plane from normal has dropped to the bottom of the implicit socket in the z direction. Another way to pull that bounding box data into this input is by simply typing implicit surface, the name of the variable, choosing bounding box, min point, and z. If you hit enter, then you see we've got the same result here, and that just eliminates the need to have to scroll back and forth between the variable in the geometry section and this block in our section below. So the min and max values in a ramp are the 2 values between which you want to see any change. So what I want to do here is begin our change at the bottom of the socket and finish it at the top. So in our in-min, I'll use the same z direction point that I used earlier. So I'll take implicit surface, bounding box, minimum point in the z direction, and hit enter. And our maximum is going to be similar. I'll take my implicit surface, bounding box, but choose our maximum point this time in the z direction. Hit enter. Now our out min is going to be the thickness that we want at that minimum z direction. So since this is going to be in contact with the rest of the prosthetic limb, I might want this a little stronger. So maybe I'll call this out min 6 millimeters. And our out max 3 millimeters. So it's a little thinner around where it interfaces with the patient's limb. I'll give it a geometric continuity. And if I isolate using I and section cut using X, I can see that the bottom of this shell is thicker than the top. So at this maximum Z direction, we've got a thickness of 3 millimeters, and at the bottom that doubles to 6 millimeters. I'll close out of this, and I'll make this a variable called thicken socket. Now, to this thickened socket, you may want to apply some sort of lattice, whether it be for aesthetics or for strength purposes. Here, I'll apply a Voronoi boundary lattice. This is going to automate a volumeless Voronoi lattice at a specified boundary. So the two inputs are seed points and mesh. Under seed points, I'm going to use a new block called random points on mesh. And for my mesh input, I'll use our surface mesh that we imported at the beginning of our geometry section. And you can modify point count, relaxation, and spatial weighting. So you see with 100 points that you have 100 relatively evenly spaced points across the mesh that we've input here. I'll probably bump that up to 300 points. If I hit enter, you can see that the number of points has tripled. Now, spatial weighting is optional, but we see that this can also be driven by a field. So I'll go ahead and add another ramp here. Or instead of a ramp, maybe let's add a point. We can make that point 0, 0, and then we'll use the minimum in the Z direction again of that surface lattice, or of that implicit surface, just to keep it consistent. Implicit surface, bounding box, minimum in the Z direction. And I'll hit enter. And under our mesh, I'll put our surface mesh once more. That's going to be where our boundary lattice is going to fall. So we see that we've got this Voronoi boundary, or this Voronoi boundary lattice created across the mesh, and it's a bit more relaxed as it moves upward in the Z direction. That's driven by this point down here. And if I use the hotkey F, I can take a look at the field of this point. I'll probe the values, and the closer you get to it, the lower it gets, and the further, the higher this field becomes. If I orient the plane so that it's consistent with our implicit surface, you can see that this gets closer and closer to 0 as we approach the point, and further as we move away from it. And that's why this Voronoi lattice relaxes as it gets further away from this point. Now, once again, I'll use a thicken body block, and I can drop this Voronoi boundary lattice straight into here, and I'll give it a thickness, let's see, of 7 millimeters. Now you see that this lattice has a 7 millimeter thickness, But maybe if I want to make this a variable, I can right-click, make variable, and I'll call that lattice thickness. I'll pull that up into my geometry section if maybe later I want to come back to it, change it around. You see that if I change it to 2 millimeters, it gets thinner, but I'll leave it at 7 for now. I'll scroll back down to here, and I can make this a variable called thickened lattice. Now, if I were to take this thickened lattice and merge it with our thickened socket right now, you see that we would have this jagged edge that could be uncomfortable for the user. So what I want to do next is just clean that socket edge up a little bit so that we can ensure comfort for the user. So to do this, I'm going to pull in another block called surface lattice. And I'll take our surface mesh that we imported earlier and hit enter. And our method is going to be our surface boundary. What this does, if I isolate our surface mesh using I and turn our visibility on down here, this is going to create a lattice that only interacts with the surface of this mesh. So if I isolate this, we can see that we've got one lattice structure up here and another at the bottom opening of our mesh. Again, we'll thicken this body and pull our surface lattice into here. And because we made this lattice thickness into a variable, we can keep it consistent and change that thickness all at once. So I'll go ahead and type in lattice thickness, choose that variable, and hit enter. Right. And now we see that our lattice thickness is 7 millimeters, which matches our thickened lattice from before. So if we turn the visibility for both parts on, we can see that now we have smooth, clean surfaces. I'll make this into a variable by right-clicking, and I'll call this cleaned socket edge. Now I'll pull a new block in here to merge this cleaned socket edge with our thickened lattice and our thickened socket. I'll use a Boolean union. And within this, we've got an implicit body list, and it has 2 different body inputs. I'll want to add a third input because we have 3 bodies to merge, and I'll pull each of these variables into our Boolean union block. Now, if I isolate using I on my keyboard, I see this final part. This acts as one implicit body now, but we can see that the lattice is also applied to the inside of this part. Now, this might not be very comfortable for the user, so I'll want to go through and clean the inside of this and leave that smooth. I'll make this into a variable, call that merged socket. And then I'll add a Boolean subtract block. And make that merged socket our primary body. And subtraction bodies, I'll want to take out that initial plug, the 3D implicit body that we made earlier. So that'll be implicit solid will be our subtraction body. If I isolate, and turn our higher resolution on to see a more accurate depiction, I see that the inside is smooth and our outside still retains that boundary lattice and our Voronoi lattice that we created earlier in this section. Finally, I'll make this a variable, and I'll call that final socket. I'll close out some of these, minimize some of these previous variables to clean our workbook up. Now, after we've created this final socket, we'll need some way to cleanly attach it to the rest of the prosthetic leg. So what I'm going to do is import a mesh of an interface cap that I created in the CAD software. And I'll use an implicit body block from mesh and create a variable, right-clicking, making a variable, and I'll just call this interface cap. Now, of course, this cap is not oriented correctly relative to the latticed socket, so I'm going to have to use a new block called orient object. The object we want to orient is going to be this interface cap, and I'll need to create a source plane and a destination plane. My source plane is going to be a plane from normal, like we used earlier, with an origin point and a normal vector. Under origin, I'm going to want the centroid of this interface cap, so I can just open up my block details under bounding blocks and pull the centroid straight into this origin point. My normal is going to be -1, 0, 0. So if we pan over here, I can see that the point is right at this centroid, and our normal is pointing straight out of this cap. Our destination plane is going to be another plane from normal. And our origin is going to be a point. Drop a point block into here. Our x direction is going to be this final socket bounding box centroid in the x direction. Enter. Y is going to be the same centroid in the y direction. And our z is going to be our minimum in the z direction so that it falls at the bottom of this, this socket. The final socket, bounding box, minimum in the z direction. I'll hit enter. So here we see that this cap isn't exactly lined up where we want it to be. So we're going to have to do a little bit of adjustment at the bottom. So first off, we see in this z direction, it's a bit far down the socket. So maybe we'll want to push it up a little further on this final socket. So instead of taking this bottom of the socket, the minimum in the z direction, we'll pull that out and we can put an add block in here. Pull that back in as operand A. And then for B, let's start by trying out 10 millimeters. So you see initially this cap was a bit lower, but now it's pushed up 10 millimeters into that socket to give it more of a seamless transition between the socket and this cap. I'll delete this empty variable and move on to the x direction. So we see here that the cap is lined up with the centroid in the x direction, but toward the bottom of this socket, we see that it could stand to be moved a bit further up along the x-axis. So similarly, I will park this chip from the X a little lower down in our workbook. And I'll put another add block here and drop our variable back into operand A, deleting our empty variable down here. Now, in operand B, I'm going to make this a variable, and I'll call that adjustment distance. If we think about this in terms of importing new patient data over and over into this workflow, this distance might vary among different patients, so I'll go ahead and make that into a variable for now. If I make this adjustment distance 9 millimeters, we can see that this cap has moved over a little bit, and it looks to be fairly centered on the bottom of that socket. I can move this adjustment distance up into our geometry section just for a bit more visibility. If I scroll back down to the bottom, I can add a Boolean union block. And pull our newly oriented object into our first body and that final socket into our second body. I'll give it a blend radius of 15 millimeters. And now we can see a smooth transition between this upper socket and the bottom interference cap. I'll isolate using I, and here is our final result. Now, like earlier, I'll go through and collapse some of this notebook just for readability and a little cleanliness. And I can move on to our leg lightweighting section. But before moving forward, let me just open this back up and remember to make that a variable. I'll call it final union socket. That'll come in handy later down the road when we create our final assembly. So under leg lightweighting, this is actually going to be quite a simple section, as lightweighting and lattice infilling are very much strengths within the Entopology software. So I will pull in this custom block from our toolkit called Shell and Volume Lattice. Now, what this does is create an outer shell of an implicit body that you choose, and it infills it with a volume lattice. You can choose lattice type, cell size, rotation, and really customize the shell and infill that you want. If you look here, you can see that there are two lines which indicate that this is a custom block. Any custom block within Entopology can be exported and read as a separate entop file. You can do this by right-clicking and selecting Export Block. That will save it to your File Explorer, and you can pull it up and treat it as you would any entop file. The shell and volume lattice is available to you through your lightweighting toolkits and can be found in this lightweighting tab. Now, if I come down here, I have a body input, so I can go up to my geometry section and take this lower leg that I'd like to lightweight. I'll drop that into our body input, and under lattice type, I'll take just a simple cubic for now. Make a cell size of 8 by 8 by 8 millimeters. And I'll leave it at its current rotation for now. Under lattice thickness, I'll start with 2 millimeters. That'll be the thickness of the lattice beams within this lattice infill. And under shell thickness, I will call that 3 millimeters for now. I won't give it a blend radius, but that could come in handy if you want to take a look at stress concentrations or strength of your lightweighted parts. But for now, I'll leave that at 0. And if I isolate using I and section cut using X, I can zoom in and see this outer shell of our lower leg and this inner volumetric lattice. I can close out of my section view and create a variable called lightweighted leg. So you can see that by using the custom block that's available to you through your preloaded toolkit, we have completed this entire section using one custom block. I'll close out of this, and we can move on to texturing the foot. Now coming down to this foot texturing section, I will create a couple of CAD list variables. So to start, I'll scroll up to this heel and isolate it using the I hotkey on my keyboard. Then holding the Control key down, I will select the heel and the bottom of the foot so that I've got these two CAD faces selected. I will remove my finger from the Control key and right-click on this highlighted blue section, and I'll select Create CAD Face List variable. I'll pull that down here into my foot texturing, and I'll rename this variable Heel Faces. I'll go ahead and do the same thing for the toe, isolating it, holding my Control key, selecting the faces, right-clicking, and creating the CAD Face List variable. I'll pull this down here, and this variable, right-clicking, will be renamed Toe Faces. And I'll hit Enter. And now we can move on to stitching these faces so that they will be treated as one CAD face each rather than two. So I'll use the Stitch CAD Faces block, and this only works for adjacent CAD faces. I'll start by deleting out this CAD face list because we already have a list made and we can't put a list inside a list. And I'll pull the heel faces down here. If I isolate, I see that this is now stitched and will be treated as one CAD face. Now I'm going to pull in another Toolkit custom block. This is called Surface Lattice from CAD Face. So I can take this newly stitched face and pull it in as our single CAD face in this custom block. My target edge length, I'll call 15 millimeters for now, and hit Enter. And you see that these two heel faces were treated as a single CAD face, and so you've got this seamless transition between the two faces. After this, we can use our thicken body block, or actually our thicken lattice block. That surface lattice in, and we'll thicken this to 2 millimeters and hit Enter. All right, and now we see that we've got this implicit body 2 millimeters thick from this lattice. Now we can take this thickened lattice and we can Boolean union to attach that tread to our heel, the implicit body of our heel from our geometry section. And if we use I to isolate, we see that this is now one body, the prosthetic heel with the lattice traction on the bottom. So we'll do the same thing for these toe faces. We'll start by stitching them, deleting the empty CAD face list, and adding the toe faces into our CAD face. We'll use the surface lattice from CAD Custom Block. Drop that down here and move our white line so we know where everything is going. And let's make this target edge length 10 millimeters, just for a little variation. And note that if you wanted to use a field-driven approach, maybe something like a point like we used earlier for our socket lattice, or a plane like we used for our shelling, then that's a possibility for these lattices as well. But for now, I'll just make that a scalar 10 millimeters. I'll thicken it like we did earlier to 2 millimeters. And then I will union that with the implicit of our toe prosthetic, going up to our geometry section and pulling that toe back down into this Boolean union block. So if I zoom out, I can see that now we've got our textured toes and heels. And I'll just make those variables to stay consistent, and I'll call that textured heel and textured toe. And now we're going to move on to the assembly section. In this section, I'm going to orient the 4 parts of the prosthetic leg, the heel, toe, lower leg, and upper hinge. Orient those correctly in relation to our latticed socket. So the way I'm going to treat this assembly is as an implicit body list. By doing this, we can orient all 4 of these prosthetic leg parts and move them as if they were one single assembly. So I'll first drop an orient object block into this workbook. And the object that I'm going to want to orient is going to be the implicit body list. I'll drop this list into here, and I'll add 3 more bodies so I can pull all of these bodies in. So I'll pull my textured toe, my textured heel, as well as my light-weighted leg and that upper hinge into this list. And I have to create a source plane and a destination plane. So I'll go ahead and turn our final union socket on just to give us a little bit of visibility. And I'll zoom out. So what we're trying to do here, if I turn this visibility for the implicit body list on, is we're trying to take this leg and connect it to the bottom of this socket. So our source plane, I'm going to want to create a plane along the top of this upper hinge with the normal facing upward so that we can attach it to the bottom of this socket here. So under source, I'll create a plane from normal. And for our origin, I'll create a point. Now, the normal of this plane is going to be -1, 0, 0. We'll hit enter. And we can see that that normal is going to be pointing outward relative to this upper hinge. Now for our X input, I'll take the bounding box of this upper hinge. So I'll type in that variable, upper hinge, select the bounding box, and I will take the minimum point in the x direction and hit enter. So now we see that the plane is lined up with in the x direction with that upper hinge. The y direction, I'm going to have to take into account that adjustment distance that we discussed earlier. So I'll put an add block in here, and I'll add the centroid in the y direction on that upper hinge. Bounding box, centroid, and in the y direction, and hit enter. And then for our operand B, I'll pull in that adjustment distance that we created earlier and hit enter. So now we see that it's centered in the y direction, taking into account that 10 millimeter adjustment that we created in the geometry section. And in our z direction, we'll take the centroid in the z direction of that upper hinge as well. Bounding box, centroid in the z direction, and hit enter. So now we see that we've fixed this plane onto the center of that hinge. Now for our destination plane, I'll create another plane from normal. And similarly, I'll put a point as our origin. And I'm going to want to take this plane that we created and rotate it and move it so that it's oriented correctly on the bottom of this socket. So what we're going to do is take a look at the bounding box of this interface cap. Let's out some of these. And if I take a look here, isolate this, I see that that's my oriented cap. I'll make a variable called oriented cap so I can use this bounding box. We can take a look at that right here. Scroll back down here, and for our x input, I'll take that oriented cap and take the centroid in the x direction. I'll take the centroid in the y direction. And then I will take the minimum in the z direction, so it falls at the bottom of that socket. And our normal is going to remain 0, 0, 1, so it's pointing up in that x direction, and I'll hit enter. And if I isolate that oriented object, and I turn the visibility back on for my final union socket, I see that these have now come together and are assembled in the way that we want. My final step in this assembly is going to be concatenating this orient object list, where the output is an implicit body list of the oriented parts of the prosthetic leg. And I'll just concatenate that with our final socket so that we have one final assembly that can be treated as such moving forward. So I'll concatenate list, pull in our oriented objects, and for list 2, I will pull in final union socket and hit enter. And I'll make this a variable and call that final assembly. So if I isolate using I on the keyboard, I have one final assembly of this custom fit prosthetic leg. Finally, I'd like to demonstrate how this workflow we've created can cut down on design time considerably once we've got everything in place. So I'll scroll back up to my geometry section and I'll import 2 new scans. This will be a solid and a surface mesh of a different patient. If we scroll in, we can see this different mesh. And this is what we're going to plug back into our workflow. So I'll rename these variables, make variable, right-clicking, make variable, and I'll call this new solid mesh, and call this new surface mesh. Then I'll replace my original solid and surface meshes in our implicit bodies. I'll scroll down in the workflow and see if we have any other areas where we've put this mesh, our original meshes. So I'll come down here to our socket creation. And we see that in this Voronoi boundary lattice, we've used our surface mesh for our seed points. So I'll replace that with new surface mesh, hit enter, as well as this mesh down here. And we've got it one more time in this clean socket edge. Enter. Now I'll close out of all of these to clean up my workbook. And this new solid mesh and new surface mesh should create a new custom fit prosthetic with our new patient data. Isolate this final assembly using I, and we have a custom fit prosthetic leg with that new scan data.